Welcome to my talk. I'm Ragavendra, a postdoctoral researcher at University and INFN Padova, Italy. I thank the organizers of Parity-violation from home for providing this opportunity, where I will be speaking about using scalar-induced gravitational waves as a probe of primordial parity violation. It is a talk based on my work with Professor Nicola Bartolo, and it is available at this archive identifier. This is the outline of my talk, where I will first briefly introduce the motivation and context of our analysis. I'll be discussing specifically about generation of scalar-induced gravitational waves in the primordial universe and induction of chirality in these gravitational waves because of the presence of primordial scalar perturbation with a parity-odd component to it. I will demonstrate my results using few parametric forms of the scalar trispectrum that contains a parity-odd component to it, and then lastly conclude with a brief summary. Parity violation in cosmology can have several observational effects. The effect of cosmic birefringence, which is being constrained better and better in recent literature using CMB polarizations, is a compelling evidence of parity violation. Parity-odd 4-point correlation functions, which is being sought in galaxy surveys, is another piece of evidence that may add to the same direction. The presence of chirality in cosmological gravitational wave background and or CMB in the form of V modes, if detected, can also add to the list of observational evidences of parity violation in cosmology. On the theoretical front, there are several theories which include presence of Chern-Simons type of coupling term in their interaction, which essentially contains a Levi-Civita tensor in the interaction, which in principle can beget one or more of the observational effects that are listed above. What we asked in our analysis is if the two highlighted observational effects here can be related in any theoretical scenario. Given the emerging analysis surrounding the parity-odd galaxy trispectrum, of which we will of course be hearing in other talks of the conference as well, we asked the simple question, if the primordial scalar sector is parity violating, can it be translated to the primordial tensor sector as well in the form of chirality in gravitational waves? Towards this end, we study the phenomenon of scalar-induced gravitational waves. Scalar-induced gravitational waves as a phenomenon is an inevitable source of tensor perturbation. It arises in a general setting of general relativity as it is sourced by scalar perturbations coupling to tensor perturbations at higher orders of cosmological perturbation theory. It provides, interestingly, an theoretical lower bound on the tensor to scalar ratio, which can be contrasted against the observational upper bound on the same ratio arising from CMB's B modes. As to the equation of motion of these SIGWs, there is a source term on the equation of motion, which essentially involves a convolution of scalar perturbation as shown here. And so the 2-point correlation of SIGWs or the mode functions shall be proportional to the 4-point correlation of the scalar perturbations. The factors I arise from the transfer function relating the primordial perturbations to late times, and the factors Q are nothing but contractions of polarization tensors to the convolved wave vectors. We can further proceed defining the dimensionless power spectrum pH lambda in the following fashion relating to the 2-point correlation. And we can also define the fractional energy density corresponding to SIGWs, which essentially gets related to pH lambda defined earlier. Note that if we perform the calculation in radiation-dominated epoch, the combination of k square eta square pH lambda, where eta is the conformal time denoting the evolution, is a dimensionless combination which is also time independent. So this pH lambda, which will be the spectral density that we'll be computing in subsequent slides, is directly related to omega GW through numerical factors. This is something good to have in mind as we proceed further. Now we turn to induction of chirality in these SIGWs. To quantify chirality, we look at Stokes parameters, specifically I and V parameters, and the associated spectral densities pHi and pHv. pHi is just the sum of spectral densities present in left and right chiral modes of SIGW, whereas pHv is the difference of the two. The degree of chirality can be defined as the ratio of pHv to pHi, and it is nothing but the relative difference between pHl and pHr. Before proceeding to compute the degree of chirality, we should bear in mind that the quantities presented here are governed by Stokes inequality, and one can show for SIGW the Stokes parameter corresponding to linear polarizations, namely Q and U, are identically 0. So V by I should be less than 1 just because of Stokes inequality. If we then turn to the term responsible for inducing chirality, the scalar 4-point function, it decomposes into products of 2-point function, which is the power spectra, and a connected term, which is the scalar trispectrum. Plugging this full contribution of 4-point function into the spectral densities, we get Phi proportional to a convolution of scalar power spectrum and a term which is proportional to the even part of the scalar trispectrum. Note that Phi shall be insensitive to odd part of the trispectrum. On the other hand, Phv shall be directly proportional to the odd part of the trispectrum. This essentially is because of the combination of polarization factors that arise in the respective integrands. To lend a physical intuition to this mathematical construction, we can imagine in the following fashion. Consider two configurations of scalar trispectrum which are inverse of each other. They are related by mirror symmetry. The first configuration, let's say, sources the chiral gravitational waves in the following fashion. It increases the left chiral mode's amplitude and decreases the right chiral mode's amplitude. On the other hand, the second configuration does the opposite. It increases the spectral density of right chiral mode and decreases that of the left. If the scalar perturbations are parity preserving, there will be equal number of both the configurations in space, and hence the imbalance between left and right chiral intensities will cancel out and we will end up with a completely achiral gravitational waves. On the other hand, if there is dominance of one configuration over the other, then we will have the resultant SIGWs with helical imbalance. And this is what we refer to as twisted echoes of an odd quartet in our paper. Now that we have the mathematical setup ready, we just have to parameterize the forms of trispectrum and proceed to compute the degree of chirality. Motivated by the models that are present in the literature, which have numerical or semi-numerical computations of the odd and even trispectrum in primordial models, we construct T-odd and T-even in the following fashion. They are, of course, triple product of scalar power spectra. The odd trispectrum is quantified by GNL tilde, whereas the even part is quantified by GNL. The odd part contains the triple product of constituent wave vectors, which essentially makes it parity-odd. This is still not a complete parameterization, as it is just a rewriting of the trispectrum in terms of power spectra. And finally, we have to specify the form of scalar power spectrum before proceeding to computation. To begin with, we consider a very simple form of scalar power spectrum and strictly scale invariant form Ps of k being equal to As. In this case, the degree of chirality just neatly reduces to the following combination of parameters of interest. Here, the factors script I are nothing but the numerical factors arising from performing of the integrations of 3 dimensions and 6 dimensions in Fourier space. What we see here is an interesting interplay in that in the denominator, we know for the case of scale invariant power spectrum, the second term should be subdominant to the first, as it is arising from trispectrum, and the first term is from the product of power spectra. So the Stokes inequality governing pi k of V by I should be less than 1 reduces to GNL tilde times AS should be less than 1, which means GNL tilde receives an upper bound of AS inverse. It may not be a very compelling upper bound over CMB scales where AS is of order 10 power minus 9. However, if over small scales AS reaches large amplitude and remains scale invariant over a very small window, then this bound shall be proportionately stronger for GNL tilde. This is the first interesting result that we got from our analysis. If we proceed to a more realistic model of scalar power spectrum of a nearly scale invariant form determined by a mild tilt and a peak, a log normal peak located at Kp of width sigma p and of amplitude Ap, then we end up with a much more richer implication for the degree of chirality. I present Phi in red curves and Phv in blue curves across a range of values for sigma p. We fix the value of Ap to be 10 power minus 2 and GNL tilde to be just 1. Even for these moderate values, we end up with pi k being at least 1% farther away from the peak. Closer to the peak, we see pi k reaching as high as 1% or even more than 1%. And closer to the peak where it falls off sharply, we have pi k reaching almost 100%. This is consistently seen across the range of variations of sigma p squared, which just makes the features either sharper or smoother depending on the values. Also, we see that the chirality alters signs between scales farther from the peak and closer to the peak, essentially because of the behavior of the integrand governing PHV. To emphasize that the large degree of chirality seen in SIGW just with GNL and GNL to be equal to 1 is not a matter of specific parameterization of scalar trispectrum. We considered a second template of scalar trispectrum in this following fashion. In some sense, it is an extension of the previous template with the introduction of an intrinsic scale dependence to the trispectrum in the form of its own log normal peak demarcated in these curly braces. It is located at KT and governed by the width of sigma t, and its amplitude is alpha. If we perform the same analysis as before and compute PHI, PHV, and pi k for this template of trispectrum, we obtain this result. What we have done here is we have fixed the width of the peak in the power spectrum to be 10 power minus 2 and have varied sigma t squared from values smaller than sigma p to larger than sigma p. What we observe is if sigma t squared is much sharper than sigma p, it strongly curtails the contribution from trispectrum, and hence PHV is significantly suppressed, especially around the peak. This results in lower degree of chirality compared to the earlier case. If it becomes comparable to the peak in the power spectrum, then it leads to an interplay between the contributions of power spectrum and trispectrum, and then we end up with such corrugated shapes around the peak of the SIGW. If sigma t square is fairly broad enough, then we essentially end up with the previous case of having the peak governed essentially by the peak in the scalar power spectrum. But beyond the specific details of various parameterization, we can consistently see the repeated pattern of large degree of chirality with just nominal values of GNL and GNL tilde for a peak in the scalar power spectrum. And more crucially, the degree of chirality is sensitive not just to the amplitude, but also to the sign and scale dependence of the primordial scalar trispectrum. This is the crucial takeaway of our analysis. And just to summarize, in the full setting of the gravitational waves being contributed by primary gravitational waves and SIGW, we have the expectation that the primary gravitational waves may be maximally chiral if the model governing is a parity-violating model of early universe. But one should be cautious that it is not always the case, as has been several examples of theories with parity-violating interaction, but still having a very low degree of primary gravitational waves chirality, as is presented in these references. But even in the case, let's say the primary gravitational waves are maximally chiral, then we have to consistently compute the total degree of chirality as a weighted sum of chirality of individual contributions, namely pi primary and pi SIGW. Pi SIGW is the computation that we have been performing so far. The weights of this weighted sum, W primary and W SIGW, are nothing but the relative intensities of the respective contributions. Now, for example, let's plug in few representative numbers. Let W primary be 96%, in that primary gravitational waves are predominant and 96% of the total contribution. SIGWs, let's say, constitute 4% with the Gaussian contribution, which is the product of scalar power spectra to PHI, being 2%, and let's say the scalar trispectrum constitutes another 2% to the intensity. We have assumed that pi primary is maximally chiral, in that it is set to 1. We should know that pi SIGW Gaussian contribution shall be 0 because it is completely unpolarized. There is no polarization contribution arising from products of scalar power spectra. Pi SIGW trispectrum may constitute a significant fraction. For the sake of argument, let's say it is -1, in that it is contributing to chirality equally but in opposite sign to with respect to the primary contribution. If we sum up, we see that the total chirality in this representative example shall not be 100%, but of course much reduced as 94% proportional to the contributions arising from SIGW. This is just to emphasize the point that the total chirality, even in cases where primary gravitational waves are maximally chiral, may not be completely 100% because of the contributions from SIGW, both from Gaussian and trispectrum contributions. So to summarize with conclusions, What I would like to emphasize is if there is a parity-violating scalar trispectrum, then there will be proportional induction of chirality in gravitational waves as high as 10% around the peak, or even in some small window of scales reaching 100%. A detection or non-detection of gravitational waves V mode shall be translatable to a constraint on GNL tilde, the amplitude of the parity-odd scalar trispectrum. Or inversely, if there is a bound on GNL tilde arising from galaxy surveys, it can inform us of the V mode that may be expected in the gravitational waves over the corresponding frequencies. With that, I will conclude and thank you for your attention. See you in the conference soon.